All right, here we are yet again for ENGR 2302 Engineering Dynamics, and this is part 2 of lecture 2 in our series here. So previously we looked at the derivative relationships and the integral relationships between the different ways of describing motion. And now we're going to work through a few example problems, seeing how we apply these things. So let's do this. Okay, so I'm going to go through a few example problems and just see how we might apply some of these equations and relationships. So my first example is going to be, the following information is going to be given. So given, a ball is tossed out of a window. And we could make this very easily a two-dimensional problem if we said it had a horizontal velocity in addition to its vertical velocity, but for now we'll stick to a simple one-dimensional motion. So a ball is tossed with a 10 meter per second upward velocity. Upward velocity from a window 20 meters above the ground. And I want to find a few things. So it's basically, there's a building, I'm tossing it out the window, throwing it upward, and I want to find a few things. And I want to do that, and we could solve this, actually, a lot of these, frankly, just via very simple equations from elementary physics class, but I want to solve a simple equation that we already know how to solve, but I want to solve it using calculus. So I could do this using just the simple equations of kinematics, or, constant acceleration kinematics, v final squared equals vi squared plus 2a delta x, those type of equations that you learned in high school, but that's too simple. We want to use the calculus. So we want to use the calculus, yes. Yes, exactly. I'm using a complicated equation to solve a simple problem. Yes, this is actually overkill for this application, but I'm trying to start us off with something fairly simple and relatable, the kind of problem you could have solved even in high school. So I want to determine a few things, or find the velocity and elevation at time t. So I basically want to be able to completely describe the motion of the particle at time t. The highest elevation reached, the maximum height, the maximum elevation, and the t it happens at, the time it happens at, it occurs at, and c, the time and velocity where it will hit the ground. And velocity of impact. And the restriction is that I do not want to use pre-derived equations. I want to do this using integration. Solve using integration. So in general, we're going to integrate twice to solve. Our approach here is that we're going to integrate twice to solve v of t and y of t. Then we'll simply solve for the corresponding time where the velocity is 0 and where the we'll solve for the time where the position is at the impact position. Okay, so let's do that. Now, so we're going to start by getting our velocity, and really we know a few things. Well, we know that, first of all, the acceleration is going to be, actually let me put this as solution here, my section. When you work through your homework, I would like you to use this sort of given, find, and solution format. So again, we're going to try to integrate twice to find, integrate twice to find v of t and x of t. I guess in this case I'll use y of t. I think that makes more sense. V of t and y of t. So here then, v of t and y of t. So I know initially that dv dt, which is equal to a, is equal to negative 9.81 meters per second squared. And then if I wish to integrate this, so let me put the, I move the dt to the other side. I should say a is equal to negative 9.81 meters per second squared.
Are we going to be using 9.1 as the standard here?
Yes, for this class, the question was, is 9.81 our standard? Yes, feel free to use 9.81 as the standard for the acceleration due to gravity for this class. Although, truth be told, if I were grading an exam and you use 9.8 versus 9.81, I really wouldn't care. And in fact, if I for some reason didn't want you to use a calculator, I could just have you use 10. But I will let you use a simple hand calculator, as we've discussed in in the discussion of the syllabus last time. Okay, so I put the dv, I move the dt to the other side, so now I'll have negative 9.81 dt. I integrate both sides, and I'm going to integrate this one from v naught to v of t, and this one from 0 to t, this one from 0 to t, and I get that v of t minus v naught is equal to negative 9.81 t. And I don't need my plus c because that's already, that cancels out. I don't have that when I'm taking a definite integral here with specific values. So then v of t is equal to v naught minus 9.81 t. Or, since I already know my initial velocity, as I described in the previous slide, the initial velocity was 10 meters per second upward. So v of t, simply enough, is 10 meters per second, 10 meters per second minus 9.81 meter per second squared times t. And that would be our velocity equation. That's the full velocity as a function of time. And I've been asked many times before, especially on exams and such, do I need units on my answers and my work? I know in some problems, especially in statics and some other engineering problems, I know it can be tedious to put units in every single step. Honestly, as long as you're consistent, I don't care if you include units all the way through. If you want it to be absolutely proper, you probably should. But the one case I definitely want you to have units is in your final result. So
we don't need to put it in every step, but we need to put it in the answer.
yes, you don't need to have your units in every, just like I did here. I kind of left off the units temporarily. If you want to do that, that's perfectly fine. Or if you're really particular about it, you can keep them all the way through. But on your final result, I would like you to have your units. And so notice the format I used. I do the same thing. I'd like you to do the same thing on your homework. Use a given, determine or find, and then solution, and then box your final result. So that's the format you'll be using for your homework. Okay, so now I want to go on and find the position function. And it's going to be very much a similar thing. dy dt is going to be equal to v is equal to 10 minus 9.81 t. And I can then, if I bring this to the other side, I can say dy is equal to 10 minus 9.81 t dt. Then if I integrate both sides, this one from y naught, I'll integrate this one y naught, and y of t. And then the other side will be integrated from 0 to t. Just some arbitrary time t. And I will get that y of t, y minus y naught, or y initial, the initial height, is equal to 10t minus 1/2 times 9.81 t squared, or simply y of t is equal to 20 meters, because now I can actually put in my initial height, which is 20 meters, plus 10 meters per second, 10 meters per second times t minus 4.905 meters per second squared times t squared. And that would be my final result for my y as a function of t. For my y as a function of time. Now I've essentially completely defined the motion of this particle. I've completely defined the motion of the particle because I have its velocity as a function of time and I have its position as a function of time. If I want to know, I can find anything I want about this particle now simply by substituting in the appropriate values of time. Okay. Then the rest is fairly straightforward. So that was the conclusion of part A. Then part B, if I want to find where the velocity equals 0, so to find peak height, set v of t equal to 0, solve for t, and that will simply be, well, I think you can handle that. If you do that, you'll get that t is equal to 1.019 seconds. Again, all you have to do is take this equation, set it equal to 0, solve for t. That's fairly trivial. And then if you want the y at that value, again, you just plug 1.019 into the y equation, and you will get 25.1 meters. I know I'm moving through that step fairly quickly, but I think I'd rather spend my time on going through more examples and focusing on the integration, because I think that's what's really going to trip you up, if anything. I think at this point you can handle simple algebra. If not, well, oh boy. All right, so then finally part C. I think that will do that. I think that'll do it for that, for part B. And for part C, to find time of impact, set y of t equation equal to 0, and solve for t. If you do, you will get two values. You will get t is equal to negative 1.243 seconds, and t equals 3.28 seconds. And you could solve that any number of ways. You could graph it, you could factor it, or more probably use the quadratic formula. Probably your best bet on an exam. But I'm going to get rid of this one. It's nonsense. We don't have negative time in this problem. All that's saying is if you projected the parabola backward in time, where else would it meet? Where else would it meet the ground? And so we know that it's going to impact at t equals 3.28 seconds. Any questions? Oh, okay. T equals 3.28 seconds. And then to get the velocity at 3.28, you simply plug and chug, and you will get negative 22.2 meters per second. Negative 22.2 meters per second. Again, hopefully fairly straightforward. All right, so let's work through another one. Okay. Let's see. So let's look at something that is maybe, let's look at something a little different. Let's look at perhaps a position or acceleration versus velocity function. So we have a shock absorber. Consider a shock absorber. And this here, so there's going to be an oil-filled cylinder. Let's see. So you have a cylinder here. And there, it's basically a piston. And it's full of oil. And so in here, so this is the piston. This is basically a shock absorber on, say, a bicycle or something like that. And this is full of oil. And so piston, oil, etc. And the acceleration of this system is equal to negative, so A equals negative kV. So a mountain bike shock mechanism used to provide shock absorption consists of a piston that travels in an oil-filled cylinder. As the cylinder is given initial velocity v0, the piston moves and oil is forced through orifices in the piston, causing the piston and cylinder to decelerate at a rate proportional to their velocity. Okay, so we don't need to worry that it's a piston. We don't need to worry through. We're not doing. This is not a fluid mechanics class. We're not working through equations of pressure or anything like that. All we need to know is that this thing starts with v0, starts with velocity v0. And basically, I want to determine, so all this is given, and then I wish to find velocity as a function of time, x as a function of time, displacement or position as a function of time, and velocity as a function of x. So that's what I'm going to do. Find and then solution. So basically my strategy is going to be, I'm first going to integrate A equals dv dt equals negative kx, and oh well, you'll see what I'll do. Basically there's a certain step I'll use to find each of these, and let's walk through this. So step one, I'm going to get v of t. 1, integrate A equals dv dt equals negative kV to get v of t. So I'm going to say that dv dt equals negative kV, and then I'm going to move velocity on one side and t to the other. So I'll have dv over v is equal to negative k dt. Just moving around my d's and my t's. Then I'm going to, because k is a constant, I can actually put the integration sign here, and I'm going to integrate this here. And I'm going to integrate from v0 to v, and from 0 to t. And the result will be then that the natural log, if I do this, I will get that the natural log of v of t over v0 is equal to negative kt. And if I apply my logarithm properties, I can find simply that v of t is equal to v0 times e to the negative kt. To use the log properties, I would say, well, it's just going to be applying your basic logarithm properties. Well, fundamentally, how I would do that is, if you don't remember, I would take both sides to the e power, and then I can simply take out the constant and go from there. All right, take out the constant and then multiply both sides by v naught. And I'm going to put a nice big box around this so I can indicate this as one of my solutions. So we now have v as a function of t. So in other words, what this is going to do is the velocity versus time, as this thing is decelerating, this is going to be an e function, or an exponential decay, I might say. So if I plotted t, or v versus time, it would look something like this. It would asymptotically approach 0, and this would be v naught up here. All right, so next I want to find x as a function of time. So any questions about how I got this? Okay, it's just a basic integration applying the integration rules we saw previously. Then, I'm going to integrate v of t equals dx dt to find x of t. To find x of t. And to do that, I'm going to first go back and say, okay, I have dx dt is equal to the v naught, let's say v naught e to the negative kt is equal to, so v of t equals dx dt equals v naught e to the negative kt. And so I'm going to bring the dt over here, and dx equals v naught e to the negative kt dt. And v naught is a constant, so I can bring it out of the equation. And then I can integrate both sides. This one from 0 to x, and this one from, oh, sorry, I'm going to put the integration sign here. Again, I can leave v naught out of it because v naught is simply a constant value. And I'm going to integrate this one from 0 to t. And if you run through your rules of integration, you will find that x of t is equal to v naught times negative 1 over k times e to the negative kt here. And this would be my position versus time function. Alternately, another way I could express this, if I wished, another way I could express this would also be, I'm not sure if I wish to or not, but an alternate way I could express this, if I didn't want to use this, is I could say that x of t is equal to v naught over k times 1 minus e to the negative kt. Oh wait, sorry, actually that's probably not quite right here. I need to evaluate this from 0 to t. Sorry about that. I need to evaluate that from 0 to t. And the final result, sorry, would be 1 minus e to the negative kt, like so. Okay. Yeah. All right, so there's that. And so this would be our final result here. All right, any questions on that? So again, I integrate it, I get this form, and then I need to take it from the bounds of t, or 0 to t, and that's what produces my 1 minus e to the negative kt. And then finally, part C, I'm going to, I want to get v as a function of x. And to do this, I am going to integrate, so part C, integrate a equals v dv dx to get v of x. Oh, and let's say a equals, this equals negative kv to get v of x. To find v as a function of x here. And so I know that acceleration can be thought of as v dv dx or equal to negative kv. So relating just these two here, let's say, how might I relate this? Well, if you look at this, if I focus on just these two here, what I can do is immediately cancel out the v's. I can cancel out the v's here. And then I can say that dv is equal to negative k dx. And I can integrate both of these. This one from v naught to v, and this one from 0 to x. Again, I left the negative and the k out because they are constants, or because it's a constant. And I can get from this that v minus v naught equals negative kx, or simply v equals v naught minus kx. And that would be my final answer. And there are other ways we could do this as well. I could also solve for this using the previous x of t relationship. Okay. So let's see here.
So the a equals v dv over dt is just something you just have to like know and memorize kind of thing.
Yeah, some of these relationships you will have to know and memorize, know how to apply them, or know how to derive them, etc. Just like you need to know that acceleration a of t is dx dt. There are some basic derivative and integral relationships that you need to be aware of, and you might want to memorize. Or if you're on an exam or something, that's probably why that's the kind of thing you might want to put on a formula sheet. Okay, so maybe one final result maybe one final example before we move on to some new material. Here, let's say I have the following system. Example 3. Let's see. Now, let us say that a bowling ball is dropped into a lake. When it strikes the water, it has an initial acceleration or it has an acceleration, not just an initial acceleration, just an acceleration. Actually, I should probably say first it has an initial velocity. That's what I was getting at, sorry. Initial velocity of 15 feet per second downward. And it experiences acceleration of a equals 10 minus 0.01 v squared. Okay? Or a as a function, this is equal to a as a function of v. A as a function of v. And so, if I want to know, if I want to determine what integral should I use, I use to determine its velocity determine its velocity when it strikes the lake bottom. The lake bottom 30 feet below. So let me draw this out. So we're going to drop a bowling ball into a lake. It has an initial velocity of 15 feet per second, and it is going to experience an acceleration that's dependent on its velocity, etc., etc. Okay? So, let's see. Now, so I have my lake here, the boat. I drop the bowling ball into the lake. Has a downward velocity of 15 feet per second initially. This lake is 30 feet deep, and I can use a positive y downward. Okay, so if I wanted to study this, well, ultimately, I am going to need okay, so here's the thing. I am going to want a x as a function of, I'm going to want effectively a velocity as a function of x, or I want a velocity as a function of x, or x as a function of velocity, something like that. So ultimately, the integral relationship I would end up with is integral of x naught to x of dx is equal to the integral from v naught to v of v dv over a of v. That fundamentally is the relationship I would want to work with. So I'll leave that to you to try to figure out why that would work, or maybe explore how you would arrive at that. But I'll leave that to your exercise this evening. Okay. So just a brief brief reminder on how we might use these types of relationships. So that's my challenge for you this evening, or for until next Tuesday. Okay. Let's see here. Now let's look at some other topics here. I think, let's see. Yeah, I would like to get on to a different topic. I think that's a good introduction to simple motion, as we've seen. Okay, so if we have I should also briefly mention uniform rectilinear motion, but I think this is fairly straightforward. If you have uniform rectilinear motion, this is really the simplest type of motion you'll see. This is again fairly straightforward. This is where the acceleration is 0. I just want to briefly mention what it is, but it's fairly straightforward. And so, because of that, dx over dt equals v is constant. It has to be because of that, because it's not experiencing any kind of acceleration. So if I integrate dx from x naught to x, and this is equal to the integral from 0 to t of v dt, well, I would get x minus x naught equals vt, or x equals x naught plus vt. So I could have a very simple relationship where if I wanted to find the position of a particle that was moving with 0 acceleration, well, all I have to do is take the initial position and then add the velocity times the time. But again, beware. When can I use this? When can this equation be used? It's a very tempting equation, very simple, but beware. Only good if acceleration is 0. If A equals 0. Nope, that is a very bad underline. So do not use that in most cases. Okay? So what if we have a slightly more complicated case where, so I'm sort of, so basically if I want to step back, what I might say is, previously I was looking at the sort of general case, and I'm looking at a few particular cases of rectilinear motion. This case is the simplest case where we have constant acceleration, or sorry, zero acceleration, constant velocity. My next special case will be when I have a constant acceleration, but a constant non-zero acceleration. So let us next look at uniform acceleration, uniformly accelerated rectilinear motion. Uniform, or you know what, or maybe I can just say rectilinear motion uniform acceleration. Uniform acceleration. All right, so let us look how this will propagate, how such a system will behave. So dv over dt is not going to be equal to 0. However, it will be equal to just a, which will be a constant. And so we'll be able to pull that out of any integrals we have. And so then if I rearrange this, I can get dv is equal to a dt, and I can integrate both of these. I can integrate this from v naught to v, and this one from a to t, and I will then get that v equals v naught plus at. Hey, that looks familiar. Remember that one from high school? Ah, that's where it comes from. But you probably saw this in your university physics class. But just a good refresher. And then I could also say that dx dt is equal to v naught plus at. So if I take this and replace v naught, if I replace v with dx dt, I could say this is equal to v naught plus at. And then if I move the dx over, or move the dt over, I can say dx equals v naught plus at dt, and then I integrate this. Then I integrate this one from, let's say 0 to t, and this one from x naught to x, and I will get that x is equal to x naught plus v naught t plus 1/2 at squared. 1/2 at squared. So we have another equation that can be very useful. This is one of our sort of fundamental constant acceleration equations, and this is another one. Pretty useful if we know how to calculate these. Then I can get another form, which if I use the relationship that v dv dx equals a, and which is a constant, I can integrate these, integrate v dv from v naught to v is equal to, if I bring the x over here, a times the integral from x naught to x dx, and I will get the other famous equation, v squared equals v naught squared plus 2a x minus x naught. And this is another of our famous high school kinematics equations. I don't want to spend too much time on them. This is fairly, this is kid stuff. So again, these can be very useful, but we do have to pay special mind and take special care to realize that these are only good for cases of constant acceleration. So again, this is only good for constant acceleration. Constant acceleration. If we try to use these equations anywhere else, we're going to have a bad time. All right, so let us look at something a little more fun, a little more hairy. So everything up to this point is simple, I suppose. Let's try something a little bit different. I'm just, spicing it up, So let us think about motions of several particles. What if we had many particles? What if we looked at, say, motions of several particles? Motions of systems of particles. Of several particles. Motions of several particles. Well, we may be interested in the motion of many independent particles. For example, you might have a system of pulleys, would be a good example. Or interconnected masses, that kind of thing. So we need to start talking about relative motion. So for example, you could have a system of pulleys that maybe there was point A here. Maybe there was pulley A, corresponded with point A, with a certain weight hanging from it. And maybe there's up here, there's another pulley hanging from the ceiling. So this pulley isn't going to move. Maybe there'd be a pulley here. This one's just hanging from the ceiling, so that one's not going to move. But then there's pulley B down here. And then maybe there's another pulley hanging from the ceiling here. And this one's not going to move. So I don't need to worry about that. I don't need to give that one a variable name. And then maybe I have just another mass here. So this is the kind of system where I might want to have I might want to look at the system or the motion of independent objects. I'm not going to call this one, I might call this one point C here. And then let me show you how the chord might go. So maybe in green I'll draw the rope. So the rope would come here, be attached to the ceiling here, wrap around this pulley, come up here, hang from the ceiling from here, wrap around that pulley, come down, wrap around pulley B, come here, wrap around the ceiling again, and then maybe attach to this pulley here. And corresponding to this, I might have 3 different x values that I'd be interested in. So I don't have numbers for this particular problem. This is just a conceptual illustration of why I might be interested in the motion of several particles. So I would have an XA, an XB, that's a very crooked X. That's a very crooked dim line. An XB and an XC, or maybe Y's or whatever I want to use. So XA, XB, and XC and XC describe the motion of independent points. Of independent objects, but they are interrelated. Maybe I should say discrete objects, maybe a better word for that. Discrete objects but their motions are interrelated. Are interrelated. Interrelated. And I probably misspelled interrelated because English be hard. Anyway. Okay. So I need to start considering relative motion. So when I start talking about motion of many particles, what this is really going to come down to is relative motion and frames of reference. Remember that term from physics? Oh boy, that's where we're at now. Relative motion and frames of reference. And this, a lot of times students struggle with this, but it's something you got to wrap your head around, unfortunately. Relative motion and frames of reference. To get the idea of a reference frame, I like to just ask a very simple question. And that question, before I get into diagrams and start labeling units or start labeling variables, I'll ask a very simple question. How fast am I moving? Me, myself, literally me. Right now.
You're not.
How fast am I moving?
Well, relative to what?
Relative to what? Exactly, that's the question. It depends who I ask. If
You're not.
I exactly, if I ask something like, so the answer, the person who is standing next to me, someone standing next to me will say you are traveling at 0 meters per second. Aside from the small bits of motion that my arms are making as I'm writing here, but in terms of the actual my center of mass, it's not moving appreciably, etc., etc. Now I could alter that if someone was standing at the center of the Earth without being crushed to death. Somehow they're standing in a magic sphere at the center of the Earth. If I could say at center of Earth. They might say, and I'm probably going to screw up these calculations, I'm just remembering some approximate figures from astronomy. I believe it's something on the order of, what is that, like 400 meters per second, I believe? I may be wrong there. Don't quote me on that. Then if I ask someone standing on the center of the center of the sun, well, they'll be screaming. Well, there'll be a plasma, so they won't be doing much. But if they're standing at the center of the sun somehow, and they can somehow see me because magic, they'll say I'm going about, I believe it's something on the order of 10 kilometers per second. But again, that's the right order of magnitude. It might be 12, it might be 14. I can't quite remember the figure off the top of my head for the velocity of this Earth relative to the sun. But it's something like that. And I'm sure we could Google it if we wanted to. And then if I asked from someone standing at the center of the galaxy, I believe the figure there is approximately 200 kilometers per second. But that may be wrong as well. Again, you don't need to know these exact figures. My point being that how fast I am traveling, that very simple question, is going to depend on where the observer is. In fact, there is no such thing as a true stationary reference frame. Nothing in the universe is stationary. Nothing in the universe is ever stationary. Yeah, nothing in the universe is stationary. There is always we can define reference frames where something is stationary, but that's just because we have defined a particular reference frame like that. Now, oftentimes we do our problems in terms of a reference frame that is at rest with respect to the ground, but there is no reason we have to do so. I mean, if we wanted to, if you really like doing a lot of integrals and a lot of math, there is no reason you couldn't do every single problem that we're going to do this semester in the reference frame declaring the center of the galaxy at rest. Although that would be some very hairy math, there is no reason you couldn't do that. It would be very complex, but there's no reason you couldn't do it. Or, for example, there is no reason I couldn't say that I could actually say, you know what, The world literally revolves around me. Literally. The earth isn't rotating, I'm at rest, and the heavens are moving around me. There's no reason I couldn't do that. The paths of all of the objects in the sky and the earth, etc., wouldn't be nice circles. They would be other very interesting equations, but we could derive those. And there's no reason we couldn't say that. I could literally declare that the world revolves around me, and I could calculate a equation of motion for the planet with me sitting at the center of the universe and everything revolving around me. There's no reason I couldn't do that. Although I think people would think I am a bit conceited if I decided to do that. So I don't recommend doing that. People tend to think less favorably of you if you try to argue scientifically that you are literally the center of the universe.
On the test, we specifically pick an annoying frame of reference and make the answer very convoluted.
If you really wanted to use a annoying but as close to a universal frame of rest that you could get, you could use the your velocity relative to the cosmic background radiation, but that is probably as close as you could ever get to a true stationary reference frame. But even that's not perfect. And oh man, you would that would be some very hairy math. Let's not do that. Let's not speak of such things again. Anyway, just the thought of doing that is terrifying me. Okay, so let's actually look at this a bit more analytically. So let us say that I'm going to look at 2 points here. Let's say I have an origin here, and point A, or object A, and object B. Object A and object B. And let me label some things, some dimensions. So I would first say that this distance here, or this coordinate, is XA, and this one is XB. And so a lot of what I'm doing here is just introducing some notation that we'll be using. And this one is from A to B, which we record as XB/A. XB/A. XBA. All right. Okay, so for particles moving along the same line, time should be recorded from the same starting instant and displacement should be measured from the same origin in the same direction. So when it's important to use a consistent unit system, basically. So always describe motion of particles in relation to the same origin, maybe spatial origin, and starting time. In other words, if I throw one ball into the air and a few seconds later throw another ball into the air, don't start time over for each one. Just have them start from the same instantaneous, have them start from the same t=0 value. So if I say, if I want to describe this, XBA, you might wonder, why did I say BA instead of AB or something? Well, because if I wanted to find this would be XB minus XA. XB minus XA. That's why it's recorded in that that format. So, in other words, we could describe this as the relative position of B with respect to A. So this is the relative position of B with respect to A. And so then XB, we could also say that XB is equal to XA plus XBA. Okay, So now now that I've talked about relative position, I might want to talk about relative velocity. So again, relative position. Relative velocity is the one that's going to be most useful, I think, but it may depend on what problem we're working with. So then, relative velocity VBA, is the velocity of B with respect to the velocity of A. So this is VB minus VA, and again, it is the relative velocity of B with respect to A. Of B with respect to A. And of course then, we could solve for VB and say VB equals VBA plus VA. And then relative acceleration, I think you know where this is going by now. The relative acceleration is going to be ABA is going to be AB minus AA. Hopefully you won't need that by the end of this class. Is the relative acceleration of B with respect to A. And that means the relative acceleration of A relative, so this is not relative to its position, but it's comparing the two accelerations. Relative acceleration of B with respect to A. And then AB is equal to AA plus ABA. Here. All right, so I think I'll work through a simple example here to illustrate the ideas here, these ideas of relative motion. All right, so basically I think that's the last topic I'm going to introduce today. I just have a few examples that I'm going to work through as time allows. Nope, that's an errant mark. Let me get rid of that. Okay. So let me run through an example problem. A ball is thrown. So let me show this here. Example. A ball is thrown vertically. Ball thrown vertically. From a 12-meter elevation. In an elevator shaft. With an initial velocity of 18 meters per second. At same instant, at same time, an open platform elevator passes the 5-meter level moving upwards at 2 meters per second. Passes the 5-meter mark, 5-meter elevation, moving upward at 2 meters per second. Okay, and so all of this is given. And then I want you to find find A, when the ball will strike the elevator. And B, relative velocity of ball and elevator at contact. Of ball and elevator at impact. Okay, so let's see here. Let me try to, if that's not clear, let me kind of draw this thing out. So basically, I have this big elevator shaft, and I initially have a ball. So here's the ground, y equals 0. And so this is the origin here, basically. And at t equals 0, here's the situation. I have the ball being thrown upward at 18 meters per second. And I have the elevator platform moving upwards at 2 meters per second. Moving upwards at 2 meters per second. And the initial heights here, the initial height here is going to be at, let's say, 12 meters. And the initial height here is 5 meters. 5 meters. Okay, and so I want to find when these, and these are basically, I didn't draw them as directly above each other, but they would be. I just drew them side to side so that you can more clearly see the dimensions. Okay, so we're going to solve that. Basically, I have a series of steps that I'm going to follow through to arrive at the solution. So, solution now. And I'm going to go through a series of steps to do this. So, 1, I will substitute the initial position and velocity and constant acceleration of ball into general equations for uniformly accelerated rectilinear motion. Okay. Substitute in initial position and velocity into equations that we derived earlier of uniform acceleration, straight line motion. Rectilinear motion. Uniform acceleration, rectilinear motion. So, VB is going to equal to V naught plus AT, which is equal to 18 meters per second minus 9.81 meters per second squared times t. And here, VB is going to be equal to, basically, I'm going to define two things. B is going to be the ball, and E is going to be the elevator. And so then I have that, and then YB, so this is the equation of the velocity of the ball at any given time, and YB is equal to Y naught plus V naught t plus 1/2 AT squared, which equals 12 meters plus, oh, that looks bad, 12 meters plus 18 meters per second, 18 meters per second, so just very straightforward substitution, times t minus 4.905 meters per second squared times time squared. Times time squared. here. Next, so that's my first step. I've gotten my 2 equations here and here, and I could probably put a box around that if they weren't so big. Okay? So I'm ready for my next step. My next step, I'm going to substitute the initial position and constant velocity of the elevator into the equation of uniform rectilinear motion. Okay, again, basically all I'm trying to do is I'm trying to get an equation for the velocity and position of both the elevator and the ball versus time, relative to the ground. So step 2 here. Step 2, substitute initial position, and constant velocity into the equations of uniform rectilinear motion. Okay, so I know that the velocity, well, our velocity equation is very simple. VE is simply going to be 2 meters per second. Problem solved, done. That was easy. Then YE, the height of the elevator as a function of time, is going to be Y0 plus VE times T, which is equal to 5 meters plus 2 meters per second times T, plus 2 meters per second times T. So then, of course, we have YE is simply 5 meters plus 2 meters per second T, with T in seconds. And that is my YE equation. All right, next, in the next step, I'll produce one of the actual desired results here. Again, I think it's fairly straightforward. Actually, let me get this. I think I'm running out of slide space here. So 3, I'm going to write equation of, actually, I probably should put this on the next slide. 3, I want to write the equation. Write equation for relative position of ball with respect to the elevator. And we get this by simply substituting, or simply subtracting the 2 equations. And then solve for when x equals 0. In other words, impact. So I know that y of b with respect to e, of the ball with respect to the elevator, is going to be yb of t minus ye of t. And this then will come to 12 plus 18t minus 4.905 t squared minus 5 plus 2t. And this will equal 0, because I'm setting it equal to 0 because, again, this is YBE, the height of the ball with respect to the elevator. And, again, it's going to be the subtraction of one from the other, and I want to know where they're going to impact. And so at the moment of impact, the position of one relative to the other is 0. And so if we do this, if we solve this then for t, I will get that t is equal to negative 0.39 seconds, and t equals 3.65 seconds. And I reject this one because it's meaningless, and instead I will accept that the moment of impact is t equals 3.65 seconds here. And then finally for here, the final step will be to say that I need to take this time value, substitute here, substitute impact time into equations of y to get the impact height and then solve for the relative velocity, VBE, to get impact velocity. And to do that, I'm going to have to create one more slide here. So I'm one short of where I need. One short of where I need. So let me copy this and then paste that. And let's just call that 34. Delete that. One short of where I need. Oh, okay, good. I'll create my slide template a lot bigger next time. So then here, if I go and do that, I want to say that YE is equal to 5 plus 2 times 3.65. Again, all I'm doing here is, I could use either equation, but the elevator one is simpler, so I'll use it. And I will conclude that this impact height is at 12.3 meters. And then the impact velocity, well, first I need to find the velocity of the ball with respect to the elevator, its equation. And this is just going to be the subtraction of, it's going to be VB minus VE, or this will be 18 minus 9.81 t minus 2, and this will then be 16 minus, so this is the actual equation for VBE, velocity of the ball relative to the elevator, or I could say it's 16 minus 9.81 t. And then if I plug in the time of impact, which is 3.65 seconds, VBE of 3.65, this is going to be 16 minus 9.81 times 3.65, or we can find that we'll have an impact velocity of negative 19.81 meters per second. And that's our final result for the day. All right, I know we went through that fairly quickly. There's a lot of material to cover in this course, so we do have to unfortunately move through a lot of this fairly quickly at times, so hopefully that wasn't too crazy. If you have any questions, feel free to come to see me during office hours. I'm available quite a bit during the semester. Send me an email if you have any questions, etc. And as always, thank you.